Hello, I'm Vincent Roykers, and this is Lab 3, Magnet. In this lab, we used a magnetometer on our phone to determine the magnetic field around an unknown magnet that was given to us. There were some main principles used in this lab. The first being that the net magnetic field of the bar is going to be equal to some constant times the distance the magnet is away to some power. In this case, the power should be close to or around 3, as this is what corresponds to the Biot-Savart law, which we also used in this lab. And in this case, we use B net is going to be equal to the constant, which is mu naught over 4 pi times 2 mu over the distance from the source cubed. In this case, we do know the distance, but we do not know the mu of the magnet. So in the case of this lab, well, we have to solve for mu. So what we would do in this lab is we would measure several points and use these points to find an average so we can get an accurate approximation for this mu. And another technique we use in this lab is that we linearize the equation of the first one to be able to solve for this unknown constant. And this would also give us, since the slope would correspond with the n, we could use this to also help us find the mu. So going into our data. Okay, so here's our Excel data. Some important things to note with this is as our distance increases here, so does our x component of the magnetic field of the bar magnet. Another important thing to notice is that this corresponds with the n as previously stated. This should be around 3. It's pretty close, but it's not exact. Some things that might have impacted this is that I did this near my computer, so that would have impacted the magnetic field because I'm doing it around an electric appliance. Also, I did it inside the building, so there's electrical wiring in the room. Okay, so now let's go look at the cliff notes of this. Okay, so going back to the important aspects of the data, since we know what our n is now, we can select any point. In this case, I chose to use the point at R20 to calculate our k value. Doing so, I got the k value as calculated there, and then I was able to use this to approximate kr to the n, and then it's just a simple case of solving for mu, which I got as the mu expressed there, 2.3114. And this is what I used in my computer model. So now let's go check out our computer model. Okay, so here's my code. What the main portion of this code is defining what the net magnetic field is. Rather than just using the magnetic moment as what we did in Biot-Savart's law, we now further define this as now we're using it as a dot product between the magnetic moment and the positional vector, as we see here. And this gives us a more accurate approximation for our overall magnetic field of the bar magnet. The rest of the code is simply just plugging in for our respective values that we have attained through our observations. And if we run this program, we see the magnetic fields pointing in approximately the directions that we would expect. All the perpendicular arrows pointing in this direction, with the other arrows going along with the magnetic field through the center. And then if we look at the D here, we see that that D is approximately equal to the D that we obtained in our lab calculations. So now let's go to our conclusions. Okay, so for our conclusions, what if I didn't align with magnetic north? In this case, it's similar to homework problems we've done before, where the net magnetic field would be some sort of vector sum between the bar magnet and the magnetic field of the Earth. Whether it's greater or less, we don't know unless we know the exact angle it is with respect to the Earth, but it would definitely impact our overall results, either being more or less than what we've gotten in this lab. And then for what if we stuck two identical magnets together, how would this impact our overall results? In this case, it's asking if we stuck them together end to end, and What's important to look at is how this impacts the magnetic moment. Upon doing further research, I found that the magnetic moment is equal to 1 over mu naught, which is similar to what we see in the constant, times some flux that represents, in this case, the magnetization of the magnet. But what is important here is the V represents the volume of the bar magnet. While sticking two magnets together would increase the overall volume of the magnet, increasing the net magnetic moment for the two bar magnets, and this would increase the moment. And then this would overall increase the net magnetic field. So in this case, I feel like it would overall just increase our results. So that's how the measurements would differ. Thanks for watching.